Hello FIT 2102 students. This is a quick video to walk you through the solutions to the week 9 tutorial code. Since it's a holiday and there won't be tutorials this week, I thought it was useful to give you the answers back in some form, but I'm doing it as a video so that it's a bit more informative than just giving you the solutions in a file. All right. So here we are in VS Code, and I am going to be running the tests like this, just using stack test. I've made it only do the functions file to start off with so that we don't get a whole lot of spurious error messages from the other file that we were to work on this week, which is traversable. So in this functions file, we have to do a whole lot of folding in different ways, very similar to how we did it in the lectures. Now, so the other thing I thought I would briefly mention is that I am using a plugin that pops up these error messages. So the plugin I'm using is called Haskero, and it's kind of flaky, so I can't recommend it. The way you first install the plugin for VS Code, the extension for VS Code, just search up here, and then the important thing is you have to do stack build intro, because it uses this intro program from the command line. You have to do that from inside the directory, the top level directory of the workshop code. All right, I've already done that, so it's going to work. Instead, we can go stack test, see that our first test is going to fail. Well, okay, there's the type hole that we made. So you don't need a plugin to see these type holes. You can equally get them by running the tests. You will see these errors, or directly from GHCI. In any case, it's telling us that the type of the thing that should go in this position here is a number. It is one of these A's, which, based on the type constraint, we've said is a number. All right, so for summing, that's our initial value, which is going to be 0. And then what goes here is a function over actually for fold R, it's the items in the list, then the accumulator, and then some operation on those two things. So summing, and that will do the trick, but obviously this is exactly the same as just passing through the plus function directly. All right, so that's summing. Product, very similar. Fold R times this time, and obviously the initial value can't be 0, because otherwise we would be multiplying by 0 every time, which would just give us 0, so the correct initial value is 1. Now for length, okay, we're going to fold again, and we're going to fold some function that simply adds 1 to our accumulator every time, like so. But can we write this in point free style? Well, obviously we can do an eta reduction on the A like that, but we still have this additional first parameter that we need to ignore every time. Now, we learnt about combinators that allow us to ignore parameters, and you will recall from the very early lectures that we had a k combinator, which is a function that takes two parameters but ignores one of them, and in Haskell, the function that is the combinator that is the same as the k combinator is called const, like so. And so that will do our length for us in point free form. Now, map is going to be copying values and prepending them onto the list. So working from the right of the list to the left, we're going to be applying some function of the items in the list and the accumulator. We are going to be prepending each item to the accumulator and building up our list like so. So is, oh, and we need a function f, and we're going to be, sorry, all I had there was a copy. Okay, now we have a map. So we are building up a new list that applies the function f to each element in the list and then prepends it onto everything we've done before. Again, working from the right-hand side because it's fold R. Can we make this point free? Well, let's see. We can obviously section, use some sections. So if we take out colon, then that allows us to get rid of this guy. That's it reduced. This looks a lot like function composition. Remember, f of g of x and is the same as f dot g, like so, which allows us, okay, to do that. And there is our map. All right. Now, filter. We are going to do something very similar. This time our f is a function that takes an a and returns a bool. So it's the function that determines whether we should include each element in the list. So if we were to write that with an if, it would be if f of I is true, then we're going to want to prepend that element on the list. Otherwise, we're just going to return the list that we're building up again, starting with the empty list. Okay. What's next? Append. So, or concatenate as we called it previously. So we're going to concatenate pairs of lists. So a list of A and a list of B, and we are going to be using fold R for that. So fold R, and we're going to take items of the list, and we are going to prepend them, and we're going to start with list B. Oops, what's wrong with that? Oh, we need an empty list. No. List B. That's better. Okay. So we are going to start with list B and prepend items from A one at a time, working right to left. Okay, that works quite nicely. Can we make it point free? Well, if we get rid of that, obviously those arguments are in the wrong order, so we're going to need to do a flip. Oops. Flip. Now we're point free there, and of course now this is just const, so we can get rid of all that stuff too. Oops, that's a bit cleaner. All right. Now, all. So all takes a list of booleans, and if they're all true, then we return true. What's that like? Well, it's logical ANDing. All right, so fold R, in Haskell, the AND operator is that, and it's very similar to the sum and the product. So we're going to need to start with true. And as long as we do that, then, and as long as all the elements in the list are true, then the final result will also be true. Any, so true if any of them are true. Well, this is going to be very similar, except this time we're logically ORing. So fold R OR over the starting value will be false because otherwise it would always be true, and that will do the trick. And finally, flatten. So we're going to take all the elements in the list and we are going to concatenate them pairwise. So again, it's a pairwise aggregation over the values in the list. So similar to all the others, do we have a pairwise operator that can aggregate lists? Of course we do. We just defined it, the concatenate. And so we're going to operate over the elements of the list, starting with an empty list, and that should do the trick. Let's check if our tests all run. And good. Okay. Okay, so now for traversable, the other file that we are going to work on, let's change our tests over to operate on that file, and we have to start off by creating an instance of the foldable type class for lists. Okay, so that requires us to implement this fold map thing. We're going to do that, well, we could do it recursively, or we could use our fold R function. And what will that look like? So here's the type of the fold map that we have to create. So fold map operates over monoids. It's accumulating a monoid, and we are going to turn the elements of the list into monoids by taking the function that is passed in, which takes the elements of the list and turns them into monoids for us, and then we know how to aggregate monoids, accumulate monoids using the mapend and mempty functions that monoid has. So our fold R will look like some function of elements in the list, and we're going to start off with the mempty. That's our empty case, and what goes here, we need a function that returns a monoid. So it's got to do everything required to combine these two, the items in the list and the accumulator, and return a single monoid. And so for that we have our mapend function. So we are going to mapend over the over A and the f of I. Okay, so that will work. Can we make it point free? Well, if we turn this around, because it doesn't really matter which order we put those, then we can see that we can do an eta reduction there. And then this looks like composition. So now it's just that. All right. Next one. Now we have to implement traverse in order to create an instance of traversable for lists. So what is the type of this traverse? Well, if we run GHCI, so let's run it outside of the stack project like that, and then we can get the general type of the traverse function, and we can see that it operates over applicatives, well, it operates over traversable things, and applies some function that takes the elements of the traversable thing and produces the result, some transformation of those elements to a type A to type B, and produces the result inside some applicative effect. What could an applicative effect be? Well, it could be all sorts of things. It could be the construction of an applicative type, like maybe or something. So that's a bit like mapping, but if we were to just map this function over a, for example, list, then we would finish up with a list of f of b's. But traverse doesn't do that. Traverse gives you back the traversable of b's all inside the applicative. So it's not a t of f of b, it's an f of t of b. So let's write that. Let's write the type of traversable here, instantiated for lists. This was more general. This was for any traversable. We're doing it specifically for lists, so we know that this type T here is going to be list. We are able, this is just a hint to ourselves and to the compiler. Normally it would work it out for itself. And in fact, normally GHC wouldn't let us put a type definition here. That would cause an error, but because we have enabled this instance extension to GHC up the top, it allows us to do it, which I'm going to do here just so you can see it. Okay, so what's the type of this traverse in this case going to be? Well, again, we're producing applicative effects, so that part is the same. But now we don't have to have a general traversable. We know that our traversable is a list, so we don't need that second type constraint. And we are going to be applying a function as before that produces an applicative effect to each of the elements in the traversable in the list. The thing we're applying it over is a list of A's, and the result is going to be the list of B's, these B's here, but with the applicative type and with the applicative container out the front. So it's a bit like an F map. Let's start off with that. Let's see what happens if we take our, so the two parameters are F and L. L is our list. If we just were to F map over the L, well, it's not going to like that because the type is the wrong way around. It's saying instead of an F of B, we're getting a list, where instead of an F of list of B's, we've got a list of F of B's. It's the wrong way around. How can we fix that? Well, actually we did that last week. We defined sequence, which, let's look at the definition of sequence, which, well, go back. We need some function here. Let's do it with a type hole. We need some function here which we can apply, which will take, a list of F of B's and give us back an F list of B's. So what has that type? Well, the sequence function that we created last week, where was it? Sequence function has exactly the type we need. And it did that by folding this lift thing. There's the lift. Folding the lift over the list. So let's go back and see what happens when we type sequence there. And sure enough, no compile error. We've fixed it. Okay. Now we have to do that for rows trees, which is, well, we're going to start off implementing fold map for rows trees. We've worked on rows trees before, so as in all those other cases, we are going to have to declare a base case for an empty rows tree, which, remember again, we're accumulating a monoid. So the base case where we have an empty rows tree is just the monoidal empty. Now, the more interesting case is when we are given a function that transforms the elements in our rows tree into the monoidal type, into the monoid, and we have a non-empty node with an element and a list of child rows trees. Applying f to the value to turn it into a monoid is trivial, and working on the list, what are we going to do? We're going to have to first, map some function over the list, and let's put some typos in here that will help us. And we're going to need something there. Okay, so what are we mapping over the list? Okay, so the list is a list of child rows trees, and this is our recursive step where we're going to need to fold map over each of those child trees. So we're going to fold map passing through the F. So now, okay, we've folded all the elements of the list by mapping fold map F over that list. But we need to aggregate, we need to fold all of those as well. How do we do that? Well, what we have now is a list of monoids which we can concat together, like so. And what goes here? We need something that takes two monoids and produces another monoid, which is obviously our map end. So we are map ending the monoid, the element in the rows tree in this node turned into a monoid, and then we are taking the concatenation, the monoidal concatenation of all the folded child rows trees, and so that's how we're aggregating over the rows tree and all its children. All right. Now, this one was tricky, and I gave lots of hints for traversing over a rows tree. As with all the things we've done over rows trees, we're going to need two cases. We're going to start with the base case because that's easy. And what's the base case? Well, remember that traverse is taking a container, in this case a rows tree of type A, with type A at every element, giving us back a rows tree of type B. So it's going to have the same structure, but with B's at all the as the values stored inside, and all that is going to be contained inside the applicative. So for nil, obviously we're going to produce also a nil. It's going to be empty as well, so that's trivial. But how do we put it inside? There's our rows tree, but how do we put that inside the applicative? Well, we have a function for creating applicatives, for putting things into applicatives, and that is pure. So pure takes a rows tree of type B, and in this case it's putting it inside the effect. Exactly what we need. Next case though is a bit trickier. So here's our function, which we're actually going to need to apply this time. Last time we had nothing to apply it to, so we didn't need it. We said we wanted to ignore it with that underscore. Now we're going to need the function. We're going to need to pattern match against the non-empty node, whose value is here, and it has a list of children, and we are going to produce something. What are we producing? Well, we're producing a rows tree of B inside the applicative. What's that going to look like? Well, we have two things that we need to work on here. First, we need to take our value and apply the function to it, just as we did for lists. So there's our f of v. Okay, so that will give us back the value. That will give us a b inside an applicative. But we need to get that inside a new node. How do we do that? Well, there's our node constructor. How can we put that, how can we apply our node constructor inside an applicative? Well, we can fmap it. Okay, so there's the first part of the problem. But then we need the result of applying the f function to all the child rows trees in this list. So we need something here. We need to, well, we can lift again. But, so there we apply the partially applied node constructor, which is inside, inside the applicative because we f-mapped it. How can we take that and apply it to, how can we take that partially applied function and apply it to something else in the applicative? Well, we use the apply. But what's the rest? What's the list of rows tree Bs that goes in the second part of the node? How can we create a rows? We need, this typehole is telling us we need a list of rows tree B inside the applicative. We're going to need to do something with that list, and at some point we're going to have to traverse an f function over this f function over here, over all of the elements over each of the rows trees. How do we do it over the whole list? Well, we traverse again. We know how to traverse over lists. We know how to traverse over rows trees. That's what that one is doing, and that gives us what we need. So now we are lifting the node constructor over a value inside an applicative and a list of rows trees also inside the applicative. And that gives us what we need. All right, so that was the end of the tutorial. That one might have been a bit tricky. I tried to give you lots of hints. Don't feel bad if it was too tricky. Don't feel bad at all if you managed to write down some reasonable questions. And hopefully once you see it, it will make more sense. All of these individual things we've seen before. This traversal of a traversal is a bit tricky, but once you realize that you are traversing over rows trees inside and traversing this function here over the list of rows trees, then it's pretty straightforward. Okay, that concludes the tutorial for this week. See you next week.